Hi, my name is Yuan. This video will presenting the Milestone 3 process. So our project is about distributed source location estimation using adaptive filter. And my other group mates are Trent Wiscom, Jordan Wu, and our world advisor is Professor John Matthew and Osama Hanedin. So for the Milestone 3, I will presenting three major parts, which is the setup, the measure, the adapt, then the combine. I know it will confuse you, but I will explain it detailedly step by step. Okay. So firstly, for the project, we will have a fixed sensors, and we will have an unknown emitter. We don't know the location of the emitter, but the emitter will sending the RF signal. We assuming the rectangular pulses. And here is three sensors, but it can be much more than that. So we know the sensor's location, and because the distance are different, the location are different. So the sensor will receive the signal at different time. So it will have the delay time. So we will get the time of arrival (TOA) for each sensors. Time of arrival 1 to n sensors, and each sensor will receive the first signal, the second, and to the end of the signal, the first, the second, third, and then yep. So because we don't know the starting time, so we cannot directly using the TOA 1, 2. So we're using another method, which is time difference of arrival. Is simply just the time of arrival minus the previous time of arrival. So n sensors will have n minus 1 time of arrivals. You may say, oh, it could be more, but all of that will be similar. So we're using just the valid value. So n minus 1 TDOAs. And time arrivals will times the speed of light will equals difference between each distance. So here D represent the distance from node K to the target, and here is the sensor L to the target distance. So when they are subtract, getting absolute value will equals time of arrival, time difference of arrival times the speed of light. So this will be the reference, and this one will be the measurement. When the reference minus the measurement, the estimate, we will get in the arrows. Okay. And for the measurements, so from the previous page, I talked about the real TDOA's time to speed of light. For the next measurements will be the decay. How is that gonna equals to? Okay, so decay equals unit direction vector UK times the target minus the sensor location. So since we're using the 2D dimension Cartesian coordinates, so sensor location will be xk, yk, and this is a fixed. We know the location, alright? And omega w0 is the target location, which is unknown, because we will set up emitter x, emitter y. Okay, so mu ki, mu unit direction vector equals cosine theta, sine theta. So theta represents the sensor location to the target. So here is the theta, okay? And in order to calculate the theta, we're using this simple method, okay? Difference between the target and sensor, delta y minus delta x. Then using the inverse tangent, we'll get the theta. So this one will be using in here. So emitter y minus y divided by emitter x minus x. Okay, this is cosine sine. Okay, so here I represent the equation why we're using cosine sine. So we're using the row vector, one row, two column cosine sine. I'm using the column vector delta x, delta y. When they multiply each other, the inner product, we are getting just one single values, right? Simple. Cosine theta times delta x plus sine theta times delta y. So we are getting d. So the numerator will be x squared plus delta y squared, which is equals to the d squared, and then divided by d will still be the d. So that's the critical point why we're using this equation instead of just theta. Okay. And for the direction, for the distance calculate, we only need absolute values because the d has to be bigger than 0. We don't want the distance is minus, right? It doesn't make any sense. So theta, when we get the inverse tangent, we might have the minus, the plus. When we get plus, we'll still theta equals theta. We'll get less than 0. The theta will be equals to minus theta. Okay. However, if we only consider the if we want to concern about another one, the angle. So the angle has to be correct, but for the distance we only need the absolute value. For the angle, it might has the negative, positive, but we will let me just explain more. Okay. So from the first quadrant, here's the sensor, here's the target. So target have emitter x, emitter y, which will bigger than the sensor location. So EMX bigger than XK, EMY bigger than YK. So the theta will in this direction. It will be fine. So theta equals theta using the inverse tangent. On the second quadrant, so here's the theta, we will get in the -1, minus theta if we're using the inverse. So we plus 180 degrees, we will get in this angle. Every time we are finding the angle is from the right side to the left side. So we're using this. The same method for the third one, we're still 180 degrees. For the fourth one, it will give us the exactly angles. It's between 0 and negative 90 degrees. Okay. Alright. For the target location, how to calculate? Once we get in the distance and the angles, we can use in the spherical coordinates, the polar coordinate, whatever it calls. So the scalar value multiply the angle. Right. We have the distance, we have the angle, so we can estimate the target. Plus the sensor location. Okay, plus the sensor location, then we will get the target. Right? Simple, right? Cosine theta times dk will equals to the delta x, this is delta y, and then plus xk, yk. we'll get in there the estimate target location. Okay. After that, we'll get into adaptation. Right now we have a reference, which is speed of light times the time of arrival. We have the estimate. Okay, we'll have the arrow. Estimate, we initially will set up, so estimate W, we can 0, 0 for the first one. So the arrow will from very big to smaller values. Okay, so from this is the intermediate step. So we are using phi, whatever it calls phi. So equals the previous target location estimate plus step size multiplied by the sum of the weight. Initially the weight will equals 1 over n. So n sensors, each sensor will have the weight, but it will getting the update, the weight will getting updated and multiply by the arrows. Every time it will getting closer to the reference, closer to the reference. Thus our estimation will getting better. Okay, using this and this. So here that will be the loop, and then we'll combine all the estimation. So WK target location equals the sum of the weights multiplied by, this is another weight, so CLK is weight, this one also is a weight, multiplied by the intermediate step. Okay, we're getting that's where the diffusion distributed estimation comes from. So it will diffuse and then combine and then getting better estimation. And we'll update the estimation of the location. Okay, so we're getting better EMX and EMY. So for our future goal is moving sensors. So sensor location is updating with time. It can be anywhere. So moving from here to here and to somewhere else, and it will still can work for estimating the target location. It's kind of robust way. Hopefully we can get in there before the technical open house. Okay. So we do adaptation, adapt then combine. That's our first step, and the future goal is adding the velocity, adding the moving sensors. So this combine will getting the update velocity and the location. Finally, we're still getting the correct location estimation. That's all I want to say for the milestone 3, and we will present for tomorrow. And hopefully it will give more definition, more details, and you guys will know much more better. Thank you for watching. My name is Wen Yuan. Thanks.